So we're going to start right here. We're changing from grade to read. Let me just remind you. Wait a second. Let me just, the last slide from yesterday was this, where we computed the so-called splitting probabilities. So this is the probability that in a finite interval, 0L, if you start at position x0, e plus exit probability to the plus side, this is the probability that you will eventually exit at x equals L. And it depends only on the initial condition, and it's this very simple Archimedes-like formula. So the closer you are to the right side, the more likely you are to be absorbed at the right side in a way that grows linearly with the distance. Actually shrink. It's linear in the complementary distance. So that's what we did last time. Now the thing is that this solution here is what I would consider the clunky, straightforward way. So you solve the diffusion equation, you compute the fluxes, you integrate the fluxes over all time, you get the answer. This is the worst way to solve the problem. And so what I want to start today is more elegant ways to solve the same problem that can be generalized to other geometries relatively simply. So the first one that I want to talk about is the so-called time-integrated or backward homomorph equation. So these are very fancy words, don't worry about it, but let me now just get to the point of how we would solve this problem. And so, formally, what we want to compute is this exit probability. And so, here, to simplify the notation, let me now know E of x. Let me have it understood. This means the exit probability to the right side of the interval. So what is the probability of exiting on the right side of the interval? What we have to do is we have to start at some initial point x. And also, to simplify the notation, I've dropped the x of 0. So the initial condition here is x. So we start at position x. E of x is the probability of exiting the right side. And so what is this? This is nothing more than the sum of all possible trajectories that end at the right side ever touching the left side. So that's what this statement is. It's a sum over all trajectories, over all paths, the probability of a path that takes me from x to L without ever touching 0. But now here comes a very nice trick, which is that we can decompose these appropriate paths in two ways. And so if I'm now thinking in terms of a discrete random walk, which hops one half to the right and one half to the left. So let's rewrite this sum over all paths as 1/2 times the sum of all paths in which the very first step has hopped to the right. So maybe let me draw a picture here. So we have our interval 0L. We're starting at some position x. And what we're interested in, and so if I think of time going this way, we're interested in summing up over all paths. So here's a trajectory, here's another trajectory. We want to sum up over all these paths and end up at L. And what I'm doing here is I'm taking my trajectories, all of them, and the point is that the very first step, you must take a step either to the left or to the right. So after one step, you're either here or you're either here. This is an x minus dx, and this is an x plus dx. And so that's what I've done, is that I have decomposed my paths into what happens after the first step is to the right. So the first step is to the right. I can think of the whole process starting over again, just one step to the right. What I need to do then is sum over all trajectories that start at x plus dx and end up on the right side of the interval. And similarly, half the time I start one step to the left, and I want to sum up over all trajectories that take me to the right side of the interval. So that's basically what's encapsulated in this equation. So one half of the time I want to sum up all paths that end up at the right boundary that start at x plus dx, and one half the sum of all paths that start one step hopping to the left and ending up at the right boundary. So this is an extremely important equation. So if you have a question on this, please ask, because everything that follows from this just follows from this equation. So I hope it's I hope this picture is clear, that I start here, and I must, at the very first step, either step one step to the left or one step to the right, at which point I have to again resum all paths from these new starting points. But now that we've written it, this sum looks very much like the original sum. And in fact, what this is nothing more than the exit probability starting at x plus dx, with a factor of half sitting up front. And this quantity, which looks very much like this, is the exit probability starting at x minus dx. So what we're doing here is actually something very powerful, which is that we're treating the initial condition as the dynamical variable in the problem, and we've written a recursion formula for the exit probability to reach the right boundary starting at x, in terms of the exit probability starting at x plus dx and x minus dx, one step in the future. And now it's a simple matter to tailor expand these two things to small dx and write a differential equation for e as a function of x. And the differential equation is really simple. It's just second derivative equals 0. You see that this is kind of like a discrete second derivative, and it actually is exactly just a discrete second derivative. And the boundary conditions here are that if I'm already at the right boundary, then by definition I've exited. And if I'm at the left boundary, then I have no chance of reaching the right boundary because I've like exited by the left boundary. So this equation has to be solved subject to these initial conditions. And this is a very simple equation to solve. And so we get x over f. So this is a really easy way to solve that problem without having to solve a full time-dependent problem. So once again, I'm trying to show you that some of these first passage questions can be solved without any recourse to time-dependent phenomena. If you want to know the ultimate exit probability, it's silly to solve a time-dependent problem and integrate it over all time. Why not solve the equivalent time-independent problem, which in this case is nothing more than the Laplace equation. So that's the same result by this so-called backward Kolmogorov equation. Why it's called backward is because the initial condition is treated as a dynamical variable. Okay. So, well, please.
Where does the second derivative come from?
Well, what I've done is I've just expanded this to second order dx and this to second order dx. So in general, for the rest of these lectures, anything which involves completely straightforward algebra, I'm just skipping over. So trust me, you just expand to second order, and you'll see that this is exactly second derivative, simple algebra. Okay. I want to now show you, in fact, in this particular case, there's an even simpler way to get the same result, and it involves a concept in mathematics known as a Martingale. And I have to say that I'm not a mathematician, so I don't know the dictionary definition of Martingale. But what I think it is that Martingale is a motion. Well, the thing is that when you have a fair game, no matter where it is stopped, that's what's called a Martingale. And in the case of this one-dimensional random walk on a finite interval, by construction, it's always fair, no matter where you stop the process. So let us compare what happens at the beginning of the process and at the very end of the process. So at the very beginning, the average position of the random walker is at the starting position. At the end, there's only two outcomes. Either the random walker is at 0 or he's at L. There's no other possibility. So at the end of the day, you have this, that either you're at, and I see it, there's a typo in this equation, either you're at 0, and the probability of reaching 0 is 1 minus the exit probability. So this should be 1 minus E sitting here. Or you're at the right interval with a probability equal to the exit probability. But by this Martingale statement that the game is fair no matter when it is stopped, the initial average position and the final average position should be equal. So, again, the same result, with no work. So this is incredibly elegant and incredibly powerful. So whenever you can apply the Martingale theorem, it works really well. And it seems that this controller here sometimes goes crazy. So sorry, I went to the next slide. Okay, let me now briefly mention what happens in the case of bias diffusion. And so this is something that I just added last night because I realized you might naturally ask, what happens if the random walk is not equally probably it's hopping to the left or to the right, but you have a probability in P, for example, of hopping to the right, or Q of hopping to the left. Again, you can calculate the splitting probability by the same backward Kolmogorov approach. And again, with it's the same idea as what you have here on the blackboard. After one step, you're necessarily either an x minus dx or an x plus dx. But in the case of bias diffusion, you hop this way with probability p, for example, and this way with probability 1 minus p, which I'll call q. But then, once you make the one hop to the right, then the process starts all over again. So here's the recursion formula for the exit probability starting at x. If you hop to the right with probability p, you restart the same process at x plus dx. Or you hop to the left with probability 1 minus p, which is q, and you restart the same process at x minus dx. And now we do the same Taylor expansions to second order in dx. And we end up with an effective differential equation. And again, I'm always skipping things now which are simple algebra, and if you want me to show afterwards, I'm not going to do it. But you end up with this differential equation, which is still a very simple differential equation to solve. And here's the answer. So now you have a somewhat more complicated exit probability as a function of x. Let me now graph this so you get a feeling of what's going on. And so what I'm showing here is the exit probability as a function of initial position as a function of x divided by L, the initial position. So in the case where there is no bias, you get this straight line behavior, x over L. And it turns out that it's much more convenient to represent things. The natural dimensionless parameter of the problem is a dimensionless ratio of bias to diffusion. And that dimensionless ratio is something called the Peckley number, VL over 2D. And so this is a measure of basically the effect of the bias to the effect of fluctuations. So when the bias is large compared to fluctuations, the Peckley number is large. Otherwise, the Peckley number is small. That means that fluctuations are dominated. So when the Peckley number is small or 0, you get more or less linear behavior. When the Peckley number is large, which means a very large bias, then if you're just very close to the left edge, the probability of reaching the right edge becomes very large. So you end up with this exponential approach for the exit probability. By the way, I should mention, for any of you who have any background in fluid mechanics, the Peckley number in random walkology is essentially the same as the Reynolds number in fluid mechanics, which is a measure of inertial effects to dissipation by viscosity. So inertia to dissipation is kind of the same as like bias to diffusion in this code. Yes?
These problems, space is, well, all space is available for the walker.
Well, here we're only doing this in a finite one-dimensional interval, so the space range is between 0 and L, and that's it.
But I was wondering in 2 dimensions,
Yep.
where the space is a disordered system.
Okay. Well, the thing is that, the point is that the formalism, the backward-Kolmogorov equation, the same formalism works in higher dimension. It's just that if you have like a 2-dimensional system, you're going to have to solve the Laplacian in 2 dimensions, generally more complicated than 1 dimension. But this same formalism works in an arbitrary geometry. It's just what can you actually solve that is associated with the Laplace equation. All right. Let me turn briefly to now the problem of Firstpassage in the semi-infinite interval. So I have the same kind of setup as before. I have a random walker which starts at x naught, and he lives in an infinite interval, except that it hits the origin, he falls off the cliff and dies. Now again, we can ask basic questions. Does he reach the origin? If he reaches the origin, how long does it take? We already know these answers because these were answered in the very first lecture, but let's look at it from this backward Kolmogorov approach. And so in the case of no bias, it's the same equation you have to solve. The nature of the equation doesn't change. It's just that the boundary conditions are somewhat different. If I'm at the origin, then it means I've already exited by the origin. So the exit probability at 0 is equal to 1. And if I start infinitely far away, that means I'll never reach the origin, so the exit probability is 0. And so this equation at an infinite interval, second derivative equals 0, that means a plus bx. And at x equals infinity, you can't have a divergent exit probability, so that means that the bx terms equal 0. So that means that the exit probability equals a. To match the boundary condition, you get exit probability equals 1. Simple. If you have a bias, Here is the associated equation, again with the same types of boundary conditions. And it turns out there's two different answers depending on whether the velocity is negative or positive. When the velocity is negative, well, since if there's no bias, we know we hit the origin. If I bias it this way, we're certainly going to hit the origin again. So that's kind of physically obvious. However, when the bias is pushing the particle away, that means the probability of reaching the origin is no longer 1. But by solving this equation subject to these boundary conditions, one gets a very simple result. Oops. Sorry. One gets a very simple result that the exit probability is exponential in this. Basically, it's the Peckley number that determines everything. So when the velocity is large, the probability when the wind is blowing you away from the origin, the probability of reaching is very small. And as the velocity goes to 0, then the exit probability approaches 1. So this Back-Homogeneous equation can be applied in many different geometries in a very convenient way to understand these basic first passage problems. Okay. I don't know where I should point this thing to make it work, so excuse me if it doesn't work. Okay, so anyways, next thing that I want to discuss now, and this is the third question in the whole menu of what happens in a one-dimensional system. How long does it take for a random walker to leave a one-dimensional system? So let me first show you the clunky way, and then I'll show you the elegant ways of solving the same problem. So the clunky way is that we have these Laplace transforms of the fluxes, and so there are these horrible cinch functions. And what we want, if we're looking at the unconditional exit time, so let me be sure I define this precisely, which is the unconditional exit time is how long does it take for the random walker to leave the interval either here or here. I don't pay attention to which way he falls off the cliff. All I care about is how long it takes for the random walker to die, and I don't pay attention to which side of the cliff he falls off. So to get the total flux, I want to sum up the flux on the right side and the flux on the left side. And now I just want to show you kind of a very general result, which is why the Laplace transform is generally so useful and powerful, which is that here's the definition of the Laplace transform. It's a total flux at time t, e to the minus st dt. And if we expand this in the Taylor series, here it is. And now let's look at this thing term by term. The integral j of t times 1, so that's the total flux leaving the system, which is 1. So the first term is 1. The second term is s, which comes out of the time integral, and then there's t, j of t dt. And I see that writing a t over here. And what is that? That's exactly the definition of the average time to leave the system. And the second term is s squared over 2 factorial comes out of the integral, and then I have the integral j of t squared dt, which is the second moment. So in fact, the Laplace transform has a lot of information inside of it because it tells you every single integer moment in the distribution. Sometimes it's called a moment generating function. So if you now take these two quantities, add them up, expand it in a Taylor series, you find this as the behavior of the exit time as a function of starting position. I'm going to come back to this again. I'm just going to rederive this so you can stare at this for a second, but I'm going to forward to the next slide because I'll do this in a different way. Anyway, just notice that the formula of this exit time is symmetric about L equal x equals 1/2 as it ought to be, and it has some interesting behaviors that I will discuss momentarily. So again, let me use this time-integrated or Back-Homogeneous approach because it is so powerful and so convenient to compute the same thing. So this should look now a little bit familiar. What I want to compute is time as a function of starting position. And again, to simplify notation, let me drop the x 0. So the initial position is now x. And let me also drop the angle brackets for average time, because we know we're talking about the average time. So what is this average time? Well, it's very similar to what we saw for the exit probability. What we want to do is we want to sum up over all trajectories. For every single trajectory, we want to count how long did it take to go this way, how long did it take to go this way, and we want to sum up all of these trajectories, the probability of each trajectory times the time along each trajectory. And once again, I'm going to break up this trajectory into what happens one step into the future. So again, if there's no bias, half the time I'll be at x plus dx, half the time I'll be at x plus dx. And let's try and re-express this in one step into the future. And in this case, you have this. So, after one step into the future, first of all, you wasted time dt. The very first step, if we're assuming that this is a homogeneous process in time, the very first step takes a time dt. So you spend the time dt taking the first step. But then you have the same process restarted from x plus dx. So hopefully this equation is familiar because it's the same as the exit probability. Or I made my first step is to the left, and so I have the time that I wasted in the very first step plus average time starting from x minus dx. And each one of these cases happens to the probability of 1/2. And now we see that what's written over here is nothing more than the exit probability. I mean, not the exit probability, the exit time starting from x plus dx. So the 1/2 comes in, that's what's sitting here, and then 1/2 dt plus 1/2 dt sits over here. So we have, again, a very simple recursion formula for the exit time starting from x in terms of the exit time one step into the future. And once again, I just do Taylor series expansion to second order dx, and one gets a very simple equation for the exit time that looks something like this. And now here comes a little bit of a subtle feature, which is that you see there are these quantities dt and dx squared. And to go to the continuum limit, what I'm going to need to do is take the limit dt going to 0, dx going to 0. I have to take that limit in a very specific way so that the ratio dx squared over dt is finite. And in fact, dx squared over 2 dt defines the diffusion coefficient when I take the discrete limit and go to the continuous. When I take the discrete equation and go to the continuous limit. So basically the equation is diffusion coefficient t double prime equals -1. So here we are with the equation we have to solve. Excuse me. So it's still a simple equation. And again, we have the boundary conditions that if I start at 0 or I start at L, then I'm at the end of the integral and it takes no time to get there. So we have to solve this very simple equation with these boundary conditions. I'm already at the edge and I'm there already. It takes no time. And the solution to this equation is this. Whoops. Sorry. I have to find the sweet spot here. So here it is. The exit time is a function of x.
Excuse me.
Sure.
About the last one. Do you know who was the first guy to write this equation? Because I have been hearing so many stories about it.
I have no idea. No, so here the history, I don't know the history of this, so no idea.
Related to that, was this continuous equation first derived or the discrete case first derived?
I'm sorry, I just don't know the history here, so who knows? Okay, so let's spend a little bit of time studying this simple formula because it has a lot of meat to it. So here I'm plotting the exit time as a function of position in the integral. So first thing to notice is that if x is L over 2, then you'll get here L over 2, L over 2, it's L squared over 8t. So first point is if I start near the middle, the magnitude of the exit time scales as L squared. And this sort of fits with the scaling we think about random walks. X squared goes like t, or t goes like distance squared. So the exit time goes like L squared. However, if I start at distance 1 away from the integral, edge of the integral, notice that this is a parabolic form, and when x is equal to 1, this is 1, L minus 1. So at the edge of the interval, it's order L. So if you're unit distance away from the cliff, and you're on a mesa of length L, how long do you live? You don't live 1, you live L time steps. And why that is that if you're at the edge of the cliff, so if the cliff is over here, half the time die right away. And half the time, well, not half the time, but the thing is that then, the very first step I'll go over here, and you can ask, what's the probability exit at the far edge? What's the probability exit at the far edge? Remember x over L. So if I start a distance 1 away, what's the probability to get to the far edge? 1 over L, exactly. How long does it take me to go distance L? It's L squared. So if I go this way, which happens ultimately with high probability, the time is order 1. But if I go all the way to the other side, the probability is 1 over L, and the time is L squared, it gives you L. And that's why the exit time at the edge is of order L. Okay, let me briefly talk about the conditional exit time, because you might say, well, I don't care, I really want to care which way I exit the system. So suppose that I want to ask, I start somewhere in the interval, and I know I'm going to fall off the cliff that side. How long does it take me to fall off that side? And again, this time-integrated approach allows you to calculate this in exactly the same way. There's actually a little bit of a subtlety associated with it. And so let me now call t plus of x. This will be the time that it takes, starting from x, to fall off the right side of the interval. And so by construction, so this is the formal definition, we have to sum up over all trajectories which start at x and lead by the right side only. And then I should divide by the sum over all paths, the probability of leading by the right side. So this is the formal expression for this conditional exit time. But the simplification happens because the denominator here, the sum over all paths, the probability that it will lead by the right side, this is what we've defined as the exit probability to the right side. So to keep my notation consistent, I'm now putting a plus sign here to denote the exit probability to the right side starting from x. So this is a little bit preliminary because now what I can do is I can take this e plus and put it on the left side of the equation. So I get e plus t plus is a sum over all paths. And now we're in a position that we can apply this decomposition one step in the future exactly as we did in the previous slide for the unconditional exit time. So I've written it in a small font because it's kind of a little bit, it doesn't quite fit. But again, e plus t plus, so it's a sum over all paths that go from starting from x to the right side, and then it's the product of the probability of the path times the time of the path. And again, everything is the same as before. It's just a little bit more bookkeeping you have to keep track of. But I go one step into the future. So when I do one step in the future, I wasted time dt going one step in the future. That's why there's a dt here. And then I have to sum up over all paths that necessarily end up on the right side of the interval, but starting at x plus dx. And then the one tricky point here to notice is that there's this e plus thing on the front. And that's because when I do this one step into the future, I'm only looking not at all paths which can lead either on the right side or the left side. I'm only looking at paths which lead on the right side. And so I have to, so when I decompose this product, the probability times the time, the first step takes the time dt, but the probability associated with that is the exit probability on the right side. So again, this summation looks very much like the original starting point. So this is nothing more than t at x plus dx, e at x plus dx, and I see also there's a notation inconsistency in this equation. There should be a plus subscript over here and a plus subscript over here as well. So I hope I'm going to remember to fix these after the fact. But anyways, the point is that by putting the e plus on the left-hand side, we see that the product et was the summation. So the summation starting at x plus dx, again, et, but starting at x plus dx, and et starting at x minus dx. And once again, we do a Taylor series expansion to the second order in dx, and we get this equation for the conditional exit time. So in order to compute the conditional exit time, it actually is a two-stage process. You first have to compute the exit probability, which we've seen is not that difficult. And once you have the exit probability, that serves as the kernel for this differential equation. And then you have to solve this differential equation. Here, this is an equation that was still very simple to solve. and it's also subject to the boundary conditions. I guess it's not on the slide here. The appropriate boundary conditions are what? Well, at x equals L, so you put x by the right side, that means t plus is equal to 0, because you're already there. At x equals 0, well, e plus is equal to 0. We're doing this condition on exiting on the right side. So the boundary conditions for this equation is that the product e plus t plus is 0, both at x equals 0 and x equals L. You work this all out, and here's the answers. So very simple looking formulas. Again, the formulas are maybe not that instructive. And by the way, I've also computed, so I've computed t plus, the t minus is just the same as sort of changing from x to x minus L as the initial condition. And so you end up with this very simple formula for the time to exit by the plus line. Let's look at these because it's more instructive to look at the picture. And so again, the unconditional exit time is plotted as a function of x naught over L. And here I plotted the time divided by the characteristic diffusion time, L squared over t. So in the case of unconditional time, this is parabolic form and symmetrical at x equals half. If I look at the exit time to the right boundary, clearly, if I start very close to the left boundary, it's going to take more time to get to the right boundary. And as you get closer to the right boundary, this exit time is going to 0 in this fashion. And t minus is just a mirror image of this about x0 equals 1/2. So again, it's a wide range of results on this finite interval problem that can be obtained very easily by this time-integrated or backward common formalism. So the thing that I want to emphasize here is, first of all, I focus primarily on the finite one-dimensional interval because it's the simplest geometry that there is to study these processes. But all these formulas will work in other geometries. The problem is, can you actually solve the Laplace equation in the appropriate geometry at hand? But things like inside of a sphere, or inside of a cone of various types, or wedges, there's all kinds of geometries that show up in various physical problems where this same formalism will work. You just have to, it becomes now a problem solving a differential equation. But I wanted to at least present the formalism in this most general formalism in the simplest geometries to get a sense of the power of this approach, and now you have to work it out in other geometries to really appreciate its generality. So any questions with what I've done so far?
In the case of
Bias. Yes.
it is equivalent to the two-dimensional case.
No, in the case of bias, the thing is that the governing differential, let's talk about the biases. It's a great question. So, I need one more hand. I do everything properly. So, we saw that for no bias, the appropriate equation was, d. So let's first of all let's do d double prime is equal to minus 1. This would be for the unconditional exit time. Unconditional. Let's just talk about the unconditional time, because for the conditional times it's more complicated. But anyways, with bias, the appropriate equation is dt double prime plus vt prime is equal to minus 1. So that's all you have to do. And again, you can derive this equation. You can start again from the recursion formula for the average time as a sum over all. We have to sum up with all paths, the probability path times the time of the path. What I did previously is the first step was 1/2 to one side, 1/2 to the other side. If I make p to one side and q to the other side, and then do the same expansion to second order, you'll see that you end up with this differential equation, and then you just have to solve it subject to those boundary conditions. So it's not a two-dimensional problem by
in one dimensional, you set that the triangle to the left and the one probability
Right.
is not equal to the right probability.
that would be in the case of bias.
Yeah, that my question was about if in two dimensional cases you can have both reactions.
Right.
And give
Okay, so I would say that all of what I've shown you here is in the case of one dimension. Let's suppose we do general dimension and do the same thing. So if there's no bias, and again, it's like the actual formulas and everything follows through line by line. One just has to, when you do one step in the future in arbitrary dimension, instead of saying a half this way and a half this way, if I'm living on a d-dimensional hypercubic lattice, probably 1 over d I go in one direction, or 1 over d in another direction. So it turns out when you do all of that, you end up with d Laplacian of t is equal to -1. And with a bias, the appropriate equation, so now I have a bias in some arbitrary direction in a d-dimensional hypercubic lattice, then it's d Laplacian of t plus v dot rad t is equal to -1. That is the appropriate generalization. Does that answer your question?
yeah.
Okay. Where am I now? Okay, so what I'll do for the next few minutes is that I want to now turn to the very beginning of studying Firstpassage in spherical geometry. And part of the reason we're going to focus on spherical geometry is that it has a lot of applications to chemical physics. And in fact, there's this whole field called reaction rate theory, which is when you have some kind of fluid, reactive fluid, and you have particles that are diffusing in the solution. When two particles come within a reaction distance, they react, and one asks, how quickly do particles react? So we're interested in what's called the diffusion-controlled limit, where when particles are within a reaction range, they react immediately, and it's transport, which is limiting the rate at which they come together. And so this is the basic thing which underlies all of chemical physics. So here's the picture I have in mind. I have a particle of radius A, and it's surrounded by a bath of diffusing reactive particles. Whenever any one of these particles hits the boundary of the sphere, it is absorbed. And the question that we want to ask is, what is the reaction rate of the sphere? And so, as you're going to see, this underlies everything in chemical physics. This very simple geometry, though, has a lot of meat to it. So even without solving any equations, there's some amazing results that we'll learn about this very simple system. So, there we go. It's very funny, like I'm pointing this way, and it's activating something over here. So the basic thing that one uses to quantify how efficient this sphere is in absorbing particles is something called the reaction rate. And so this is nothing more than the particles absorbed per unit time. But the thing is that if I have twice as many particles over here, there'll be twice as many particles absorbed per unit time. So to get an intrinsic measure that depends only on the absorber itself and not on the external system, we divide by the concentration of particles externally. So this quantity, the reaction rate, is number of particles absorbed per unit time, per unit concentration. So that's the basic quantity. Now again, in these sorts of problems, dimensional analysis gets you a long way. So without solving any equations, let's just do like high school dimensional analysis on this equation, and we're going to learn something quite remarkable about this reaction rate. So let's look at the dimensions of the reaction rate. So number has no dimensions. Per unit time, so that is 1 over time, and 1 over concentration. Concentration is number per unit volume, and so 1 over concentration is units of volume, or its length to the power d. So that's obvious. But now, what can the reaction rate depend on? What are the basic parameters in the system? And I argue that there's only 2 parameters. Can someone help me and tell me what are the 2 parameters in the system?
The radius A.
Okay, that's one. Good. What's the other one? What? No, but the number of particles has been divided out because of this dividing. So there's one more parameter still working. What? Excellent. Diffusion coefficient. That's all that depends on. So this reaction rate is a function only of the diffusion coefficient and the radius of the particles. There's no other parameters left in the system. And again, it's one of those things that when you're doing dimensional analysis, it takes a lot of effort to get to the very first base. And once you've got to first base, then you basically have a home run because all the information is contained inside. By the way, if you want to know, so this is a complete digression, but I just thought I'd mention is that the most amazing example of dimensional analysis I've ever seen is that when the very first atom bomb was exploded in the Alamo test, some magazine showed pictures of the size of the blast rate as a function of time. And a guy named Jeffrey Taylor, who's a very famous fluid mechanicist, took these pictures, which said like at 0.01 seconds it's this big, at 0.02 is this big. And he, from those pictures only, inferred the energy released by the bomb, which was obviously a top military secret. And he got hassled by the OSS, which is the forerunner of the CIA. How did you find out this military secret? You spy. And it turns out dimensional analysis, just from those pictures, you can derive everything. And if someone wants to know, I can show you. Anyways, but now the thing is that let's now do dimensional analysis on the elements that go into the reaction. Here. So the dimensions of A, well that's length. The dimensions of the diffusion coefficient is length squared over time. And now what we want is this reaction rate, which depends on length and depends on the diffusion coefficient. We somehow have to jigger it so that it has the units of volume over time. Clearly, the reaction rate has to be a linear function of the diffusion coefficient, because here's the only time in the system, since there's 1 over time here and 1 over time here, the reaction rate must be linear in the diffusion coefficient. But because it's linear in the diffusion coefficient, that means it's got 2 powers of length. We want d powers of length. So to get d powers of length, we've got to multiply by a to the power of d minus 2 to get d powers of length. So here it is. The reaction rate is proportional to the diffusion coefficient times the radius to the d minus 2 power. And this actually is the correct result. But this simple answer already has some very strange features. So let's just look at this in various spatial dimensions. And typically we're interested in 3 spatial dimensions. So in 3 spatial dimensions, the reaction rate is linear in length. Let me emphasize that. The reaction rate is linear in the radius. It's not proportional to the cross-sectional area. So if you think about Rutherford scattering, where you have electrons coming into a charged particle, or let's just forget about Rutherford scattering. Just think about geometrical cross-section. So you're trying to hit a target. When you're playing darts, you're trying to hit a target. So the probability to hit the target is proportional to the area of the target, not its radius. But here, the rate at which this target absorbs diffusing particles is proportional to the length. So let me put 2 exclamation points here to emphasize. Think about this. It's really bizarre. If the particles are moving at a finite velocity, the reaction rate is quadratic in length. But when they're diffusing, the reaction rate is linear in the radius. If we look, though, at less than 2 dimensions, well, 2 dimensions itself is special because it's 0, so there's logarithms going to float around. But for less than 2 dimensions, then you see that when the dimension is less than 2, the reaction rate depends on an inverse power of the radius. That says that if the radius goes down, the reaction rate goes up. So what the hell is that? And that's why I put 4 exclamation points, because it's something very different happens in less than 2 dimensions, and in fact, the reaction rate is not defined properly in less than